Hello everyone, I'm Jiqing Zhang, a PhD student from Dalian University of Technology. Our paper title is Multi-Domain Collaborative Feature Representation for Robust Visual Object Tracking. This work is jointly completed by Dalian University of Technology, Advanced Institute of Information Technology Peking University, and SIR International. This paper focuses on effectively representing and utilizing complementary features from the frame domain and event domain for boosting object tracking performance in challenge sensors. Usually, the visual object tracking will specify a target object we want to track with a bounding box like the red rectangle. Then the tracker will search the target object in the following video frames and give a new location to better locate the target object by adapting its location and scale. This setting is simple and works well in regular scenes. However, RGB-based trackers suffer from bad environmental conditions, for example, motion blur, low light, high dynamic range, and so on. Event-based cameras are well-inspired vision sensors whose working principle is entirely different from traditional cameras. Instead of capturing images at a fixed rate, they asynchronously measure per pixel brightness changes and output a stream of events that encode the time, location, and sign of brightness changes. An event camera has independent pixels that respond to changes in the log photo current. When the change of the log value reaches a temporal contrast threshold C, an event will be generated. The event contains TXYP, where T is the timestamp, XY is the pixel coordinates, P is polarity, which indicates the increase or decrease of brightness. In summary, an event-based camera is a novel sensor that measures only motion in the scene. The advantages contain low latency, no motion blur, high dynamic range, and ultra-low power. However, since asynchronous event format differs significantly from the frames generated by conventional frame-based cameras, traditional visual algorithms designed for frame-based cameras cannot be directly applied. Through the above analysis, we found RGB trackers suffer from some challenge scenes, and the advantage of event-based camera provides the potential to solve this problem. We observed that events and RGB data are captured from different types of sensors, but they share some similar information, like target boundaries. At the same time, static event images and RGB images have their own unique characteristics. In particular, RGB images contain rich low and high frequency texture information and provide abundant representation for describing target objects. Events can provide target attributes that are not influenced by motion blur and bad illumination. Therefore, event-based data and RGB images are complementary, which calls for the development of novel algorithms capable of combining the specific advantages of both domains to perform computer vision in degraded conditions. At present, there are mainly two ways to process event data. One is to aggregate events into frames and then process them with traditional methods, and the other is to directly process event data with spiking neural networks. In this paper, we primarily explore combining SNS and CNS for visual object tracking. RGB-based tracking, that is, standard object tracking, is one of the hotspots in the field of computer vision. Over the past few decades, the research on target tracking has made considerable progress. The most representative methods are CFMOS and deep learning. Despite the fact that event-based object tracking methods can benefit a lot from the high spatial temporal resolution and high HDR features of event cameras, there are only a few works done in this area. These works can be roughly divided in two categories. The works in the first category need a clustering process to group events into clusters. The works in the second category do not need the clustering process. To improve the tracking performance, multimodal-based tracking approaches have been getting more attention. Most of the works leverage depth or thermal. Depth is an important key to help solve the occlusion problem in visual object tracking. Illumination variations and shadows do not influence images from the thermal field sensors. They thus can be combined with RGB to improve performance in degraded conditions, for example rain and smoke. Unlike these multimodal approaches, combining frame and event domains brings a unique challenge caused by the asynchronous outputs of event-based cameras. Our approach aims to solve the problem and effectively leverage the event domain for improving robustness under degree conditions. As RGB and event share some similar information, such as target object boundaries, we propose a common feature extractor as a consistent strategy. We first stack event stream according to the current and latest time step of positive and negative polarities, which makes vision algorithms designed for frames can be also applied to asynchronous event streams. The stacked event count image contains the number of events and each pixel, which implies the frequency and density information of targets. The stacked event timestamp images contain the temporal cues of the motion, which implies the direction and speed information of targets. An example of current images and timestamp images is shown in figure B2E, and the corresponding RGB is A. To balance effectiveness and efficiency, we apply the first three layers from the VGG9M as the main feature extraction structure of our CFE. Specifically, the convolution kernel size are 7 times 7, 5 times 5, and 3 times 3. Since the raw event stream and RGB data storage methods and expressions are different, it is necessary to design an exclusive feature extraction method for each domain. For the RGB domain, we propose unique extractor for RGB to effectively extract unique texture and semantic features. Specifically, as shown in the first figure, UER consists of three convolutional layers. For the event domain, since SNN can process raw event stream directly, we introduce it into our unique extractor for events to effectively extract unique event features. Spiking neural networks are bio-inspired models using spiking neurons as computational models. The inputs of spiking neurons are temporal events called spikes, and the outputs also are spikes. Spikes are short pulses of voltage surge and distribute their effects in time to form a post-synaptic potential. The magnitude and sign of the post-synaptic potential is determined by the synaptic weight corresponding to the spike. Finally, the accumulation of all the post-synaptic potential in a neuron constitutes the subthreshold membrane potential. This process is illustrated in the last figure. When the subthreshold membrane potential is strong enough to exceed the neuron threshold, the spiking neuron responds with a spike. Immediately after spike, the neuron tries to suppress its membrane potential so that the spiking activity is regulated. This self-suppression mechanism is called a refractory response. In this paper, we adopt SRM to describe the dynamic of a spiking neuron. After extracting common shared features and unique features from both domains, we fill them with a concatenate operation. Considering different video sequences have different classes, movement styles, and challenging aspects, we further use three fully connected layers to process fusion features. FC6 is a domain-specific layer. That means each training has key sequences and then there are key FC6 layers. Each of the key sequences contains a binary classification layer with soft cross attribute, which is responsible for distinguishing target and background. It should be noted that we didn't use a very deep network or complex integration strategy because of the following reasons. First, compared with visual recognition problems, visual tracking requires much lower model complexity. because it aims to distinguish only two categories of target and background. Second, since the target is usually small, it's desirable to reduce the input size, which will naturally reduce the depth of the network. Finally, due to the need for online training and testing, a smaller network will be more effective. Our main principle of network design is to make it simple yet work. We believe that more and more related works could be done to further improve such a compact network. The following are our training details and tracker details. Supervised learning for visual object tracking requires a large quantity of data. In our case, we need a dataset that contains RGB data and events with ground truth bounding box. Our dataset needs to meet the following needs. First, the RGB image and event-based data must be aimed at the same thing, and the data between different domains must be aligned. Second, we must have a large variety of scenes with ground truth bounding boxes to avoid overfitting to specific visual patterns. To our knowledge, such datasets do not yet exist. In order to meet the above requirements, we generate a synthetic dataset using Event Camera Simulator (ESIM) on large-scale short-term generic object tracking database (GOT). To demonstrate the effectiveness of our method, we first test it on the standard RGB benchmark (OTB). From the results, we can see that our method outperforms the other trackers on OTB. It demonstrates the effectiveness of our structure for extracting the common features and unique features from different domains. In order to analyze what reliable information the event-based data provides, we report the result on various challenge attributes to show more detailed performance. These are visual results. To further prove the effectiveness of our method, we also evaluate on the real event dataset (EED). The EED was recorded using Davis event camera in real-world environments, which contains the event sequences and the corresponding RGB sequences for each video. The EED also provides a ground truth for targets. The EED contains 4 sequences that are fast join, letter variations, what is a background, and occlusions. The quantitative results are shown in this table. We can see that the traditional RGB trackers are severely affected by low light and fast motion. When there is too much noise in the events due to lacking image texture information, the event-based texture cannot effectively obtain satisfactory performance. Instead, our method can effectively handle high dynamic range and fast motion conditions. To verify the effectiveness of multi-domain, we implement 3 variants, including MC, FROE, OR, and ER that are only use events, only RGB, and both events and RGB as inputs. The result illustrates that using multi-domain information is indeed superior to a single domain. We remove UEE, CFE, and UER respectively to validate the effectiveness of our network. We also explore the performance impact of different ways of stacking events. Our method does have limitations. The failure examples are shown in red finger. Since the target is static, the event camera cannot effectively provide the edge cues of the target, resulting in unavailable information. In summary, firstly, we propose a novel multi-domain feature representation network which can effectively extract and fuse information from frame and event domains. Secondly, we preliminarily explore combination and design for visual object tracking. Finally, the extensive experiments verify our approach outperforms other sort methods. The application studies evidence the effectiveness of the design components. Thanks for your attention.